Circle geometry, angle at center, part 1 of 2. Let's think about an angle at the center of a circle. So O is the center, there's the angle at the center. Produce the arms of that angle to the edge of the circle. Now we're going to have a bit of terminology. This arc here subtends that angle there, and it's very easy to see because have a look at the shapes of the arc, and I'm going to keep mentioning these shapes. They are parallel shapes, if you can get curved parallel lines. They are parallel to one another. So we can make the angle bigger and the arc gets bigger, but this arc still subtends that angle at the center. We can switch to the other side. So now we have, because it's this angle here, we must follow the arc with the same curve. There it is there. This arc subtends that angle. Now, a bit of background. Let's have a look at a couple of examples back from grade 7, grade 8, Euclidean geometry. This first one, there's an isosceles triangle. Now, being an isosceles triangle, we know therefore that we have a 20 degrees there. And hopefully you'll remember that if you take a triangle and produce or extend one side, you form an exterior angle. That exterior angle is equal to those two inside angles added together. Quite simply because x adds with that to get 180, and those two add with that to get 180. So therefore x must be the same as those two combined. And therefore x is 20 plus 20, 40 degrees. Let's put that on the side. Just as a reminder, that's why the heaps. And here we will have the same situation, but two angles. So 30, 40 and 60, 80, same reasoning as in the first case. And that makes that whole angle 140, which is quite interesting because this whole angle is 70. 140, 70, double. Well, that's logical, hopefully, because 60 is equal to 30 plus 30, and that 80 is 40 plus 40. So if this is double and that is double, the whole thing must be double. And there's your angle at center. Let's put this one on the side now. Let's go a step further. Instead of now having two separate angles, we'll say, what's the size of that angle there? Well, isosceles triangle, exterior angle triangle, and therefore 88 degrees there. And notice 44 degrees there. Double. If we take the angle at the center in a circle now, this is the previous diagram, we have the same sort of situation. Where now we don't know the two parts, though, to that angle. But in fact, consider us here, we don't need to if you look at the reasoning there. And that angle there is going to be double this angle here. And there's your angle at center. So the angle at center says the angle which the arc of a circle subtends at the center. So there it is. Notice the parallel curves is double the angle subtended on the circumference. And it's got to be on the remaining part of the circumference because we don't want this angle to be sitting on the arc because then we'll have the wrong curve. The curves won't be parallel any longer. So anywhere on the remaining part of the circumference. So the angle at the center must have its arms firmly established on the circumference. The angle on the remaining part of the circumference must have its arms firmly established on the circumference and, of course, at the same point as the angle at center. And there the two lines, one line to signify double. We can move this point P anywhere. If I moved it down to the right there, it's still double. We can move it up and then down to the left on the other side, right down there. And it is still double, still double. This angle is still double that. They still are subtended by the same one. All right, this might not look the same as that, but take it around and you'll see it's still the same curve as that one. This one here, same situation, where instead of having down on the right or down on the left, we've now got straight through to there. This is still double that. In fact, this is the first type of example we did a little while back. This one here, there's the angle at the center. That being the curve, there is the arc. So in fact, there's the remaining part of the circumference. So anywhere there on that remaining part of the circumference, there's point P. Draw the angle up there. That parallel. Here's another one. There's the arc. There's the angle at center. There's the angle at the circumference. So let's just talk about on the sideline first thought processes. If I had found x there, then how would I go about that? Well, there are two ways I can do that. There is the hit or miss method, where all we do is we just try to find as many angles as possible and hope that we hit the x. Here's the hit or miss. Yes, here we go. Oh, all these angles. Wonderful. Gets very confusing. Obviously, I'm exaggerating it a bit. I've found every angle in the figure. But we just try to find angles until we can see x. And that's the hit or miss method. I call it haphazard, which means without any system at all. And talking about systems, method 2 is systematic. Let's think back to our childhood. When you saw in the Sunday newspaper a pirate map in the kiddies section, and you're told find which path leads to the treasure here, and there are 1, 2, 3, 4, A, B, C, D, different points through which the paths start. I don't believe that any one of us tried A's path, tried B's path, C path, D path until we got the right one. Come on, I'm sure that you went straight to the treasure and followed it back the other way. There we are, C. Now, why can't we do the same in geometry? If I'm trying to find x, let's start at x and let's take a path back until we hit something we know. So we say, well, what is x equal to? Well, it's equal to that one there. Now look, this is a slightly longer path than we needed to go, but I'm trying to show the method, that's why. Right, isosceles triangle. So now I say, well, what is this equal to? I'm being patient. I still haven't found x, but I can keep going finding other angles equal to x or combining with x. What is x equal to? Well, there we are. The parallel lines. Alternate angles, parallel lines. Now we say, well, what is this x equal to? We're getting close to the 62 degrees. Well, there we are. It's equal to that because it's an isosceles triangle. Now, at that stage, we cannot find any other things that x is equal to. But x can combine. We say, well, is there any way x can combine with anything? Well, have a look at this situation. There is your triangle. There is your produced side. There's your exterior angle. Aha. Those two add up to give you the 62 degrees. Making x 31 degrees. And there's the systematic way to go about it. So, let's just go back to remind you, pick up a pattern in a very corny way. Notice, there's an angle, there's the arc, there's the angle at center, angle at circumference, and I've spoken about this. Notice that all these sets of curves are parallel curves. So we're very happy about that one, because those are fun. But when we look on the other side there, have a look at the black curve. It's always going against the flow. It's just the opposite. So therefore, in fact, that is going the wrong way, wrong way, wrong way, wrong way. We're not happy about that one. So we need these for angle at center. We don't need this to happen. So we don't talk about this angle and an angle down here, because this will go that way when that is going that way. So let's have a look just at these examples. The first case. There we are for x. Have a look at the matching lines. Let's have a look at y. Notice the curve is going this way. So therefore the matching lines all go that way. And x, the curves go that way. So therefore all the matching curves go that way. For x in this case, there's the curve there. So don't take 180 to 110 because have a look. It's going the wrong way. This curve would not be parallel. So therefore we need to say, well, what's the parallel curve there? There we are. In number 4, be very careful. This is the first case where we have this. X is not an angle subtended by an arc at the circumference, because have a look at the arms of x. This one only goes to the center. It does not go to the circumference. This is an angle subtended by an arc. Have a look to there, to there. So this angle is subtended by that arc. That's fine. So that x, we could say, well, hopefully it's equal to that one, because that one definitely does have a link to the center of the circle. We have a look at this one there, that angle there. Once again, this x is not subtended by an arc, but that angle is, and it's linked to other angles. This next one, x, that's fine, it's subtended by an arc. There we are, all going in the same direction. This x on this side, that's fine. That there, notice, there we are. And finally, that x there, there would be the angles. I wouldn't be very happy in this one saying what is x equal to, because in fact x is equal to half of y, but y we don't know either, so that's not taking us anywhere. So I'd have to say, well, what is y equal to? And coming back to twice x. So we'd have to look at another method there. Let's look at the first one. Find x. Straightforward. 124 is twice x. Reason. And here's the reference for angle at center. Angle at center. Some people write, just put a circle with a dot in the middle as well. Angle at center. There might be other ones as well. Try not to use a verb in a reason in Euclidean geometry, because I always tell my students that using a verb in a reason is writing an essay. All the theorems have references. They don't have to be the same reference as the next teacher uses or something like that. They could be slightly different. I mean, angle sum triangle, sum angle triangle, they all mean the same thing though, and you need to show what you're talking about and include all the necessary parts. So angle at center. So therefore x is 62 degrees there. This next one there. Well, we can find y straight away, because have a look at the red curves. That's fine. Y is half of that. The x, I'd have to find this angle before I could find the x. But remember, there is a very simple reason why BOC is 116 degrees. Angles at a point. Sum of angles at a point, angles round a point, as long as you show what you're talking about. Now, there's the curve, and they're both from the same arc. So therefore, 116 equals 2x, angle at center, and therefore x is 58. The y is very straightforward, because that 244 is equal to twice y. Look at the curves. And the reason angle at center, so y is 122. This one here, well, yes, the curves are in the right direction. We don't know that, so we need to know that one first. So there we are. Angles at a point, and therefore we can find x. This one here, that x is not equal to any other angle by angle at center or circle theorems, but that x is equal to c there. Alright, so if we said what is x equal to, x is equal to c, and we can find c. See there the greens? So what is x equal to c? Aha, we can find c. 70 degrees equals c. Why? Well, angle at center. So 2c, that is. 70 degrees equals 2c. So c is 35 degrees. And x is equal to 35 degrees then. Alternate angles AQ parallel to BC. Remember that alternate angles alone is not enough of a reason, because you can have alternate angles without the lines being parallel. You must say alternate angles, corresponding angles, cointerior angles, and then state the parallel lines. Y 70 degrees. Straightforward alternate angles, AQ parallel to BC.